right, welcome back to statistics. So today we're going to talk about binomial distribution. This is section 6.2 in our book. This can be a little involved, and there's a few calculations that we'll go over. The calculator is going to end up dealing with most of the heavy lifting, and we're going to kind of go through like what you need to do on a calculator in order to get this thing to work. So the thing I want you to remember is, like, don't be intimidated by it. Okay, it is going to look intimidating at first, but a little bit of practice, you're going to be just fine. All right, it's important to know like what to look for so you know what kind of problem it is and when to apply this thing. Okay, so let's go ahead and share the screen, and we'll go on for this. Okay. So the first problems kind of talk about, they're going to reinforce stuff that we're going to talk about first. Okay, so we have binomial distribution. Mostly what you're looking for, okay, how do you tell? It's two outcomes. Okay. They don't have to be numerical outcomes, okay? So for statistics' sake, okay, we could have boy, girl, vice versa. I mean, technically, what we're doing is we're saying it's boy and then not boy. Okay. So to keep things simple, okay, I know there's non-binary people and they're their own category too. But I don't. We're going to set those aside for the moment, just so we only have two options. But if you don't want to set them aside, it's boy, not boy. So if somebody doesn't identify as a boy, we can just say you're not identifying as a boy, which could be girls, which could be somebody who has their own identity. Okay, or somebody who does a boy. You identify as a boy, you're in this category. If you don't, then you're not in this category. Okay, and just go back and forth. Okay, heads, tails. Okay, we have married, not married. Okay, even, odd. Okay, anything where you have two categories. All right, and it could be things like, on a die, I could do 1, 2, 3, 4, and then 5, 6. So I have the category of things that are 1, 2, 3, 4, and then categories of 5, 6. All right, so that's our two categories of things. Okay, they could be numbers, they don't have to be numbers. All right, so the next thing we're going to talk about is we have two outcomes. We have a set number of trials. Okay, that means we're going to have a family with 4 children, boy, girl. We're going to flip a coin 6 times. You're going to interview 7 people to see whether they're married or not married. You're going to roll a die 10 times. Does it come up even or odd? Okay, so it has to be a set number of times. So we have a set number of trials. Okay, the probability of success. So we have two kinds of what the outcome that we're looking for. We generally call that successes. Again, we're not putting some kind of an ethical or a good bad idea on success. There are sociologists, they study tobacco use in children. If you ask like a bunch of 12th grade, not 12th grade, yes, ask a bunch of 12-year-olds whether or not they've tried tobacco, and you're interested in how many people have, like technically the yeses are a success, but like having 12-year-olds try tobacco is not really a success. Okay, so we call them success, fail. Okay, what else do we have? We have independence. Okay, so you need to set up this thing so that each of the trials are independent. Okay, if you're going through a grocery store, you're talking about how long people stand in line. If you ask like the first 3 people in that line, if you've been here, like what's your wait time? Like, do you think that the people after them in line are going to have similar or longer wait times than the people that showed up, or the people that are already in line? Like, yeah, that's not independent. Going back to my tobacco experiment, sorry, I grew up in the 70s and the 80s, so back then smoking was cool. But if you ask 3 12-year-olds if you've tried tobacco, and those 3 say yes, no matter how many more you ask, what's the answer the rest of them are going to give you? They're all going to say yes. It's not independent. Okay. You have to ask them confidentially. Okay. So you want independence of thing. You also want, this is kind of related to it, the probability of success is constant. Okay, so the probabilities are not changing. So you could draw cards, as long as you're putting them back, that's going to be, they're going to be independent, and that's going to be constant. But if you start drawing cards and keeping them, like, there's fewer cards that are going on. So no matter what you're looking for, right, their denominators are going to be 52, 51, 50, 49. This is changing probabilities. Okay, the denominators are changing. So the probabilities are changing as you go through. So that's not a constant number. Okay, they're moving. Okay. So those are things you have to watch out for. Okay, so your P, your probability of success, that's constant. You have a set number of trials or attempts. Okay, you can't decide like, wow, we were going to go 3 out of 5, but that didn't work out, so we're going to go 4 out of 7. That didn't work out. We're going to go, just keep moving that up. All right, you can't do that. You say, we're going to interview 12 kids to see whether or not they tried tobacco. We're going to flip this coin 10 times or 6 times, whatever it is. But you have to have a set number of trials. Okay, you need that 2 outcomes. That's really your big thing. Okay, and then you have to have independence between trials. All right. So our first little problem here, okay, is state the, okay, so let's see here. Determine whether or not a random variable X has a binomial distribution. If it does, state the number of trials. If it doesn't, explain why not. A fair die is rolled 30 times. It doesn't have to be a fair die in this case. Let X be the number of times an odd number appears. So yeah, this is a binomial distribution, right? The die is, each roll is independent. It doesn't depend on the last one. Whether, regardless of how many numbers are on the die, right? It's always going to be the same. It's the same die, so probability of getting an odd number is always going to be the same. Okay, we have a set number of trials. I said we're going to roll it 30 times. Okay, and there's 2 outcomes, right? You don't know any numbers that can be even or odd, right? 0 is even, by the way, because 2 times 0 is equal to 0. And if you try to do like 2 times 0 plus 1 or 2 times 0 minus 1, these are not 0. Okay, so there aren't any numbers where you could add 1 to it and then, 2 times a number plus 1 or 2 times a number minus 1, that's never going to get you to 0, assuming that n is a counting number. Okay, so you can't put in half because that's not an n. That's a rational. Okay, so it does have, right? This variable has a binomial distribution. Okay, oh, there's a problem. Hold on, let me reload my thing here and I'll be right back. All right, there we go. So in this case, they changed it a little bit. 6 cards are drawn randomly with replacement, so we're putting them back from a standard deck of 52 cards. Okay, by the way, that's an American standard deck. Some other countries, like I think Argentina, uses a different number of things in their deck. Let X be the number of aces that appear. Okay, so let's see here. we do have a binomial distribution, mostly because of the replacement thing. Okay, because that's going to keep our probabilities constant and are independent. Okay, we're saying randomly drawn, so we're assuming that we shuffle between the draws, etc. Okay, so let's go ahead and check. All right, and the number of draws. How many cards are we drawing? We're doing this 6 times. Okay, so the scenarios: we're drawing a card, looking at it, putting it back, shuffling it, looking at the card, putting it back, shuffling it, looking at the card. We're doing that 6 times. We're not drawing out six cards in a row and then looking at them, because that's changing the probabilities as we go through it. Okay. So there we go. All right, so that's what happened. All right. Let's see here. All right. Okay, good. All right, now we're going to go through the formula. Okay, so this is going to take a little bit. I'll show you how to do this in the calculator as well. So we want the binomial. So we're going to say the probability that capital X equals little x. I hated this notation when I was learning statistics. This is the random variable. This is the instance of thing you're looking at. So the probability that x equals 1, probability that x equals 7, something like that. Okay, capital X is the random variable. The little x here, this is the probably this is the actual value that you're looking for. All right, so I'm sorry for that notation, but that's where it is. Okay, so we want an n choose. Let's go with this. N choose x. Most of the calculators and most other books say this is n choose r. Okay, your face-to-face counterpoint, they voted on r because that's what their calculator wants you to use. So we'll use r for the most part. Okay. What does this mean? This means how many ways. So we're not trying to list those ways. We're just saying how many times can it happen? How many ways can you choose r things from a collection of n things? So examples would be, I have 5 pieces of candy. How many ways are there for you to pick 3 of those pieces? Okay. I have 5 colors. How many ways are you to pick 2? I've got, we have 18 students in the class. How many ways are there to pick 4 people for a committee? Okay. Now, one of the things we have to deal with is that our the number of things you're picking is that order doesn't matter. Okay, order does not matter. So we're not picking a president, a vice president, a treasurer, and a secretary kind of a thing. Okay, we're picking 4 committee members, and all of those members have the same power. Okay, so there isn't any ordering. And it's like, well, how useful is that? Like, well, if I order a pizza and I said, I'd like mushroom and pepperoni on my pizza, will I know if the person who made that pizza put mushrooms and then pepperonis like I asked for? Or if they put pepperonis and then mushrooms, will I ever be able to tell that difference? No, we can't tell. So it's just, we're not implying an order as the first one to get picked was best or anything. We're just saying, how many ways are there to pick them? Okay. The other way we do this, so the notation here is 5, choose 2. Okay. Your calculator will say 5 NCR 2, right? We're choosing, we have a collection of 5 things. We want 2 of them. Okay. So why do you pick 5, choose 2? I mean, we could pick 13, choose 8. Doesn't matter. Okay. But I'm going to do 5, choose 2 because we're going to count them. Okay. So we have black, white, red, green, blue. How many ways are there to pick 2 of these colors from this selection of 5? Okay, so black will be B, white will be white. We have red, green, blue will be U. Okay, so how can we do this? So we have black and white, which is the same as white black. Okay, so it doesn't, if you're gonna, think about this as a chess, like it doesn't matter. We've got pawns of both colors. Okay, we have black, red, black, green, and black, blue. Okay, black, red, black, white rather, black, red, black, green, black, blue. And we have white, red, white, green, and white, blue. Okay, and then we have red, green, and red, blue. And then we have green, blue. Okay, those are all the different ways to pick this if the order of the color doesn't matter. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ways to do this. Okay, here's the formula. Okay, so again, I'm sorry for the length, but I like to explain this like all the way through before we get to the technology and the calculator, and I say press these buttons. That's coming, but hang with me for just a little bit. Okay, so the formula we use, we say this is n, one of those, n minus r, and n r. Okay, this thing means factorial. Okay, and then what a factorial does, okay, how to compute the factorial. So if I want 4 factorial, we're not just talking like it's a 4, but it's really excited. No, it's 4 times 3 times 2 times 1, and then we calculate that out. And what about 0? Okay, what a factorial does, it's counting how many different ways there are to arrange things. Okay, so if I have 0 numbers, how many ways are there to arrange it? There's one way. You can just point to it. We're already done. We've arranged it. Okay, so same thing with 1. If I have no pieces of candy, how many choices do you have? I say, if I had some candy here, I'd offer you one. Like that's nice. Technically, that's a choice, right? But it's not a very interesting one. I've got 1 piece of candy. You can pick whichever one you want. Right? You have any color of car as long as it's black. It's a heavy Ford thing. So if you have 1 factorial is just 1. Okay, a lot of people just give up with this, say 0 factorial is equal to 1. We're done. It's good enough. Okay, there's also a way using calculus to get this as well. Okay, so there's also a calculus method. But for now, right, it's 1. You can think it's how many ways are there to arrange no items. There's one way. You just look at it. It's like, hey, I've got an empty plate. Like, that's great. That's my choice. So that's where we are. So we're going to say this is 5 factorial, 5 minus 2 factorial, and 2 factorial. Okay, this is my n. We have 5 colors. We're trying to pick 2 of them. Okay. You cannot ever distribute this factorial through anything. Okay, it doesn't work that way. You have to do it inside the parentheses and then apply the factorial. You cannot distribute the factorial anywhere. All right, so this is 5 times 4 times 3 times 2 times 1. That's my 5 factorial. Okay, 5 minus 2. 5 minus 2 is 3. So we need 3 factorial here, right? So this is 3 times 2 times 1. 2 factorial. That's 2 times 1. Okay, so let's go ahead and do some of this. So we have 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. 3 times 2 times 1, right? That's 6. 2 times 1, that's 2. So that's 120 over 12. 120 over 12 is equal to 10. What do you know? The astute student would probably look at this and say, wait, can't you cancel? Like, sure, you can cancel. It's like 3's, 2's, 1's. So we have 20 over 2, which is 10. We get the same answer. It's okay. You're allowed to do that. Okay, but maybe you didn't see it. It's okay. All right. A lot of times people write this like we'll write 5, choose 2. 5 allows students to write NCR2. Okay. And then the books that I use do it this way. And I'll try not to do this too much. I'll probably try to keep it this way because it's our 21st century notation, but our 20th century notation is here. Okay, so it's 5 over 2 with the parentheses. There's no fraction bar, so it's just that's just read 5, choose 2. Okay, so that's how you choose things. So binomial, okay, probability that x equals r, right, is NCR, right? 5, however many trials you have, choose the number of successes you're looking for. Okay, P to the R, P to the number of successes, your probability of success. Okay, N is number of trials. Okay, and then we have 1 minus P. Some books will call this Q. Okay, to the N minus R. Okay, so we do our first couple of calculations. I'll walk us through what's going on here. All right. I shouldn't say this on the internet because it's going to be here forever. I know whatever I was doing when I learned this stuff, I think I was watching a lot of mafia movies. And the question that always comes to me here is like, hey, I see you have 10 fingers there. How many ways are there for you to lose 3 of them? So just in case you get in deep with a loan shark and they ask you, you could answer this question. And it probably is not going to work out well for you, but you could answer it. All right, binomial experiment has been given a number of trials N and its probability of success P. Okay, and here we go. Determine the probability of P or the N is X is equal to 2. Okay, answer to 4 decimal places. So we want probability X equals 2, but we know that we have a binomial. We have N is equal to 8, P is equal to 0.5. Okay, so let's put this together. We have 8, choose 2, right, because X was 2. We have, what's our probability of success? 50. Okay, how many successes are we looking for? 2. All right, you put down 50, something costs 50 cents. All right, you're at a convenience store, something costs 50 cents. I know, go with it. You put down your dollar, how much change are you supposed to get? 50 cents. That's how we figured this out. This was 1 minus 0.50. Okay, that's what this was. We have 8 attempts. We have 8 experiments. 2 of them are going to come up successes. How many do we have left? We have 6 of them remaining. Okay, and that is going to be how we set this thing up. All right, now calculators, because we could do this, right? This is 8 factorial, 8 minus 2 factorial, 2 factorial. This is 1/2 squared and 1/2 to the 6th. Oh, that looks delightful. Calculator. So what we're going to do, okay, is this choose thing. This is so common. It doesn't even matter. Well, it barely matters what calculator you have. It's actually in your calculator. So if we were to do 8, choose 2, right, we're going to hit 8. You're going to come over to here where it says math, okay? And then we're going to scroll across the top using our arrow buttons to where it says PRB, right? And then you see where it says NCR here? That's what we're going to do. We want NCR 8, NCR 2, okay? 8, choose 2. And hit the equals button. Okay, that's 28, okay? You have 8 things. How many ways are there to pick 2 of them? That's 28, Okay, I don't know what they are. I don't want to list them. That seems like a lot. But there are 28 different ways to select 2 items out of a collection of 8. So your friend has 8 pens. They said, hey, I did too many pens. Pick 2 of these. There's 28 ways you could go. Okay, then we're going to have 0.5 squared and then 0.5 to the 6th. So 0.5 squared is not going to be too bad. It's 0.5, press the little square button, boom, 0.25. All right, and then times. Now what we're going to do for the other one is we're going to say 0.5 caret. We need this button right here. Okay, it's right underneath the clear button. Okay, caret, that means raised to the 6. All right, well, I said this is 0.015. 625. All right, these are all times together. So we have to times them all together. So we're going to say 28 times 0.25 times nope, not that, 0.015625. All right. And our answer, our probability here is was 1. No, it's not 1. 0.109375. 109375. How many decimal places did they want? They wanted 4. So we're going to go with these 4. Okay, so this is 0.109. The 7 turns that into a 4. All right, and there's our answer. I should make a liar out of me. 0.1094. Okay. Oh, we wanted the leading 0. Okay, find the mean. All right. This is one I would generally expect you guys to memorize this formula, that the mean of a binomial distribution is, well, let me ask you. If I know that the incidence of a household having a dog, not in my neighborhood, it's a lot higher, but overall, the probability has a dog, and I'll say has at least one dog, and I say that that is 30%. Okay, I go to 100 houses, and I walk on the doors of 100 houses, and I count how many times I am met with barking at the other end of that door. How many times would you expect I would hear barking if I knocked on 100 doors, and there's a 30% chance that there's a dog behind one of those doors? You would expect that to be 100 times 0.3. You would expect that I would hear a barking after 30 doors. Okay, how did we get that? Well, we took the 100, that's n, times p, right? Times the 30%, 0.3. Change that. Make that, you can actually read it. Okay, times 0.3. That's how I got the 30. This is n times p. So the mean is NP for binomial distribution. Okay, it's probably going to ask me for standard deviation in the next one. I would never expect you guys to memorize standard deviation. Okay, it's 2. I never asked it. So that's not true. I only asked it when we used to do note cards, which I don't do anymore, to make people waste space on their note card. Like, I'm going to ask you what the standard deviation is. You're going to have to write this down. So we have 8. P is 0.5, so 8 times half, right? That's 4. All right. Find the variance in the standard deviation. See, I knew it. So standard deviation is the square root of n times p times 1 minus p. Don't memorize this formula. I will let the homework ask you, because it will often. The homework can figure out what's going to ask you on this. Okay, so that is 8 times 0.5 times 0.5, and we're going to take the square root of this thing. All right. So what's half times a half? Half times a half is a quarter. What's 8 times a quarter? All right. 8 over 4, that's going to be 2. Okay. Do they want decimals? Probably. 3 decimal places, fine. So all we have to do is figure out what's the square root of 2. So second function square root, second function 2, not that 2. 2 equals, we got 1.414. Okay. How many decimal places do they want? Run the variance to 2, standard deviation to at least 3. Okay. So 1.414. 1.414. You know what the variance is? Variance is a standard deviation squared. What's the square root of 2 squared? Don't overthink it. Right? This is 2. So the variance is 2. Standard deviation is square root of 2. All right? And that's all they want out of that. All right. Let's see here. All right. 2 or fewer. We could do this one. We'll use the calculator when it actually matters. Okay. So we have n is equal to 13. Probability of success, 0.2. Okay. I don't know what this is about, but they always like when it's like a word problem. But they want to know what's the probability that x is less than or equal to 2, right? 2 or fewer. That's what this means. So what we have to do is we have to figure out what's the probability that x equals 2, probability that x equals 1. Actually, let me change that. Instead of an x, let's change this to an r to be consistent with what we were doing earlier. So r is equal to 2, r is equal to 1, probability that r is equal to 0. Okay. So we're going to set these up, and then we're going to use the calculator to figure out the values, and then we're just going to add those values up. Okay. So setting up, we have 13. Choose what? Choose 2. Okay. We have 0.2. How many successes do we want? In this case, we want 2 successes. I know nothing costs 20 cents, but if something were to cost 20 cents, you put your dollar on the table, something costs 20 cents, how much change are you supposed to get? That's 80 cents, right? So this was 1 minus 0.2. Okay. That's what that was. So we're going to run 13 experiments. We had 2 successes. How many failures? How many experiments do we have left? We have 11. Okay. And we're going to calculate what this is. R is equal to 1. So we still have 13 trials. Choose one of them. Okay, we're going to get 1 right. Okay, 0.2. How many do we get right? 1. 1 minus 0.2 is 0.8. We have a total of 13 experiments. We've used up 1 of them. How many do we have left over? 12. All right. And then here we're going to have 13, choose 0. Okay. I have 13 pens. You can't have any of them. How many choices do you have? 1. That's a nice collection of pens you got there. Okay. 0.2 raised to the 0. 0.8 raised to the 13th power. Okay. So let's run through our calculator here. So we're going to have 13 math. We're going to scroll over to where it says PRB and then down to where it says NCR. Okay. NPR, okay, not the radio station. That's a permutation. That's when order does matter. So if you have to select a president, vice president, treasurer, secretary, that's the permutations. We want combinations. Okay. So NCR, we want 2, right? NC2. Okay. Actually, let me do one thing. Let's go ahead and insert a parentheses here. End it with a parentheses. So it does this part first. Times. If you want to use parentheses after this, that's fine, but 0.2 squared. Oops, I went squared. Exponents will happen before multiplication, so the 0.2 squared will happen first. This will happen, then we're going to multiply the 2. Actually, this will happen first, this will happen second, then we'll multiply the 2 of them. Times, what do we have? We have 0.8 raised to the 11th power. Okay, again, exponent will happen first, then we'll get around to the times. Okay, well, what do we get? We got 0.2680. All right. Next, we have to add these up. Okay, so we're going to say 13. Oops, we're going to put parentheses in. 13, right? Math, all the way over to where it says PRB, down to NCR, enter, 1. It's going to be 13, by the way, times 0.2. Do we need an exponent here, or is it just raised to the 1 already? It's already raised to the 1. You don't need the exponent. It's not going to hurt anything if you put this in here like this, okay? But you also don't need it. Okay, times 0.8 raised to the 11th power. I'll be right back. All right. So where were we? NCR times 0.2 times 0.8 raised to the 12th power equals. Okay, we're going to write that down. 0.178. This is a 7 here, so we're going to round up. So 1787. All right, this one's going to be a little bit easier. We have parentheses. We have 13. Okay, we're going to hit math over to PRB, down to NCR, choosing 0, so 13 choose 0. Okay, times 0.2 raised to the 0. Okay, anything raised to the, well, any non-zero thing raised to the 0 is going to be 1. Right? And then times 0.8 raised to the 13th. Done, done. So 0.054. Actually, this looks like 0.055. 0.550. Okay, look, do the rounding. We're going to add those up, right? Because that is the probability of none, 1, and 2. Those are the numbers that are less than or equal to 2. Okay, so here we go. We have 0.2680 plus 0.1787 plus 0.0550 equals, so about 50%, so 0.5017. Okay, let's hope we round it in the same spot. You never know. Okay. So 2 or fewer, go back here, 5017. 0.5017. All right. Fingers crossed. Hooray. Find the mean. Round answers to 2 decimal places. Okay. Again, the mean is nothing more than n times p. All right. So we have a total of 13 things times 0.2. All right. So it should be 2.6, I believe. So 13 times 0.2, 13 times 0.2. Hey, look at that, 2.6. All right. Back to here. 2.6. You want to bet they're going to ask us for mean and standard deviation next? Variance and standard deviation. Gotta love it. Okay, so sigma squared is equal to n times p, 1 minus p. Sigma is equal to the square root of n times p times 1 minus p. Okay, so this is 13 times 0.2 times 0.8, and this is going to be the square root of 13 times 0.2 times 0.8. Again, don't memorize this formula. I only used to ask it just because we would let them use a 3x5 card. And quite honestly, this was just to use up real estate on a 3x5 card. Like if I figure, like, well, I'll give you a 3x5 card, I might as well give you a reason to use it. Here, write this down. So here we go. So this is 13 times 0.2 times 0.8 equals 2.08. Right? I'm not going to ask this. The homework asks it enough times. Okay, so we're just going to take the square root of our previous answer, equals 1.4422. All right, so let's go ahead and take a look at our problems here. All right, so we want 2.08 here. 2.08, standard deviation, 1.4422. Okay. It says at least 3 decimal places, so technically that's not, they might complain. Oh, they didn't. Look at that. They took it. Good for them. All right. All right. So at this point, I'm going to go ahead and give it an intermission, and we'll have a part 2. And the part 2 will be, we'll start the calculator on part 2. All right. So thank you for sticking with me, for doing all of this stuff by hand, or at least a minor calculator use. We'll do more major calculator use in the next section here. Okay, so I'll be right back. Good luck.